All right, welcome. And now we're going to start our study of determinants. And so we're going to use determinants. We're going to show how they're useful. We've already seen how they can be useful in 2x2 cases, but we're going to even build off of that and add more. Okay, but before we do that, let's talk about a couple of things that we've learned along the way, specifically with square matrices. Okay, and how it relates to their singularity or non-singularity. And in this case, non-singularity. So T of n sub n, let T be an n by n matrix. What we find is this square matrix is non-singular if and only if each of the following holds. Any system T times vector x equals a vector b has a solution. So that system has a solution, and that solution is unique. Gauss-Jordan reduction of T yields an identity matrix. The rows of T form a linearly independent set. Also, the columns of T form a linearly independent set, a basis for R sub n. Any map that T represents is an isomorphism. That was another result. And of course, the final result and the most recent one that we found is that an inverse exists if T is non-singular. And so now what we're going to do is investigate more, because one of the first things we're going to ask is whether a matrix, when we're dealing with a square matrix, is whether it's non-singular or not. Okay, so in this study of determinants, we're going to develop a formula that determines whether T is non-singular. More precisely, we're going to develop a formula for 1x1 matrices, one for 2x2 matrices, and so on. Now these are obviously related, so one of the things we're going to develop is a family of formulas and a scheme that describes a formula for each size. And so going on, what we're going to do is we're going to restrict, as we're talking, we're only going to be dealing with square matrices. So as we're talking about matrices, we're not going to keep saying square matrix or square matrices, we'll just simply say matrices. Okay, and so now let's get started.